Hello, my dear students. Welcome back to one more videos lecture on econometrics. In last video, we were discussing about the problems of the OLS assumption. There are certain cases where the assumptions of OLS may not hold. Okay, and such situations known as the problems associated with or major problems in econometrics, especially in major problem with the regression analysis. Okay, so we have discussed the multi-collinearity issues. Okay, and we have also given some of the basic idea about the problem of heteroscedasticity. Okay, so heteroscedasticity is a problem associated with the error terms. Okay, so most of the time when we use cross-section data, the variance of the error term may not be constant for all observations. Okay, so in such cases we have a problem of heteroscedasticity, and if we have a problem of heteroscedasticity, then in blue properties the B will not stand. That means best or efficient property will not be satisfied. Okay, and we have seen how we can mathematically solve, or how we can mathematically prove where this efficiency condition is not meeting. And we have also seen certain other problems with this heteroscedasticity, like confidence interval will be very wide. Okay, as a result, standard error will be biased, and F and t-test is likely to produce uh, unreliable results. As a consequence of these things, the OLS results obtained from the regression analysis may go misleading or may go wrong. Okay, so that was the consequences of this heteroscedasticity. Now, coming to how to detect whether there is an issue of heteroscedasticity or not. We have run a regression analysis. We have run a regression. We have obtained the results. Okay, then all the significance, when we check the significance about all the parameters seems good. Okay, then we have to check whether there is an issue of heteroscedasticity or multicollinearity. Okay, and specifically to heteroscedasticity, how we can check whether there is a heteroscedasticity problem or not. Okay, yes, so for that, what we can do, actually, we have told I have told you that the variance of the error term is equal to small I square. Okay, and the small I square can be known only if we have the entire population. Okay, in our examples we had entire populations. Okay, so in each different income groups we had different observations, then it is very easy to find out its variance. Okay, but the premise that most of the time we have only sample, we don't have the populations. Okay, so with a single observations we cannot find out the variance. Okay, the variance can be find out for only a group of observation, not for a single observation. Okay, but when we take the samples we have only one observation, and due to this fact this small I square is not known in the case of samples. Okay, so how we can find out variance of a sample? Okay, so the heteroscedasticity problem is simply a matter of induction or guess or prior empirical experience. Okay, so it is not very easy to find out whether there is a heteroscedasticity problem or not. Okay, and it is basically a matter of intuitions. What is the matter of intuitions? It means that when you take the consumption and income analysis, okay, if all of your sample respondents have have almost equal level of income and equal level of consumptions, then you can say that there will be no problem of heteroscedasticity. Okay, but in your samples some people or highly rich, some people are very poor, then you can see, you can induce that there may be certain level of heteroscedastic problems. Okay, yes. So since if we are dealing with the samples, then heteroscedasticity will be simply a matter of induction or guess. Okay, or we can tell something about the heteroscedastic problem if we have a prior empirical experience. Okay, yes. So the first method to detect the heteroscedasticity is the graphical method. Okay, so in graphical method, what we have to do, first first step you have to do is do a regression and obtain u cap square. Do a regression and obtain u cap square. Okay, then plot this u cap square against the estimated y cap, or plot u cap square against y cap. Okay, and you have to plot the squared error term or u cap square on vertical axis, and you have to plot the estimated y or y cap on the horizontal axis, and you have to check whether there is any systematic pattern. Okay, and if there's a systematic pattern, there will be a problem of heteroscedasticity. So what you have to do, take the value of u cap square, take the value of y cap, plot u cap square against y cap, and check whether there is any systematic pattern or not. Okay, so here what you mean by the systematic pattern, these are all certain systematic patterns. Okay, yes, and you look at the first graph here, we cannot find any systematic pattern. There's a pattern but it's not systematic. Okay, but when you look all this data, all this graph, all this graph having a systematic pattern. Okay, all this graph having a systematic pattern, but in the first case there is no any systematic patterns. Okay, even though they are horizontally plotted or horizontally dotted, it is not a systematic pattern, but in all other cases we have a systematic pattern. Okay, so if you are getting a graph like A, then there is no problem of heteroscedasticity, but if you are getting a graph like B, C, D or E, then you have to think that, or you have to assume that there is a possibility of heteroscedastic problems. Okay, yes. And apart from this graphical test, from the graphical test, we cannot actually tell there's a problem of heteroscedasticity or not. Okay, it will give some idea or some basic idea about the problem of heteroscedasticity. Okay, so what we have to do, we have certain tests. Okay, we have certain tests like Park test, Gluster test, Spearman rank correlation test, Goldfeld-Condit test, BPG or Bruce-Fagan-Gottfried test, and White general heteroscedastic test. Okay, so we have a number of tests for detecting the heteroscedastic problems. Okay, so these are all some of the major tests. Okay, so what we do, we will discuss all these tests one by one. Okay, first we'll go to Park test. Okay, Park was an econometrician. Okay, so what he has done, he has formalized the graphical method. Okay, so he borrowed the idea of the graphical method, and the graphical method he has converted into a formal test. Okay, and he suggests that this small sigma I square is some function of the explanatory variables xi. Okay, so the small I square is a function of xi. Okay, and suppose small sigma I square is equal to actual variance, okay, into x raised to b and e raised to vi. That means it is following a what function is this? Exponential functions. Okay, That means whenever the explanatory variable increases, the variance is also increasing exponentially. That's why we are taking an exponential functions. Okay. Then if you take an exponential functions that is non-linear, you cannot estimate it using OLS. So what you have to do, we have to take a log transformation of these models. When you transform this model into a logarithm, what we will get, this small I square will become ln sigma I square is equal to ln small sigma square or ln variance plus beta ln xi plus vi. And you run a regression by taking variance as your dependent variable and xi as your independent variable, and you check whether this beta is significant or not. This beta is significant or not. And if beta turn out to be significant, then there is a problem of heteroscedasticity. Okay, so what we have to do, we have to estimate a regression models in such a way that you take some small sigma I square as your dependent variables and xi as your independent variable. But here there is a problem. The problem is this ln small sigma I square is not directly observable, because we have a sample only. If we have a population, then we can observe this, but we have only samples. Okay, so instead of these things, what we have to do, the Park suggests that if you don't know this value, then you take these values. Okay, so you take ln u cap square as a proxy for ln small sigma I square. Okay, so what you have to do then, you have to estimate a normal regression like yi is equal to beta 1 plus beta 2 xi plus ui, and you have to capture u cap and u cap square. Okay, then ln u cap square is equal to ln small sigma I square. This is nothing but the this is nothing but intercept. Okay, plus beta ln xi plus vi. You run a regression like taking u cap square as your dependent variable and xi as your independent variables, and check whether your beta coefficient is significant or not. Okay, if it is significant, then there will be a problem of heteroscedasticity. Is it okay? Yes. Now let me check it how we can do these things using real data. Okay, so first let me take this Park test. Okay, first you take the Park test. Before, what we do, we will check whether graphically whether there is a problem of heteroscedasticity or not. Okay, then this is your y and this is your x. Okay, then what you have to do, you have to find out the value of u cap square and y cap. Okay, for that there is a very simple step in in Excel. What you have to do is go to data analysis, regression. Okay, you take the y range, you take the x range, you put label. Okay, and here there is an option residuals, standardized residuals, residual plots, line fit plots. Okay, where you put residual plots or residuals. Okay, then you can paste the output here itself. Okay, x range is missing. Yes. Okay. Yes. Now, if you look the equations, we have got intercept is 17 and x is 0.6. Okay, and when you drag to downs, you can see there is a predicted y and residual y. That means the Excel will automatically generate the residual as well as your predicted values. Okay, so what is this predicted y means what? Your y cap. Residual means what? Y cap. Sorry, u cap. Okay, then what we have to do? We have to find out u cap square is equal to, this is u cap, and if you square it, okay, if you square it, you will get the values. Okay, then this already there. Okay, then you copy this both and you paste it here. Okay, then you select both and insert a graph for that. What type of graph you have to plot? You have to plot a scatter plots. Okay, so from this, what we can understand? Can you observe any systematic pattern from this graph? From this graph, we cannot observe any systematic pattern because the dots are scattered something around. We don't have a shape here. Okay, the graph is not showing any systematic shapes. Okay, so what we can do, we can assume that there is no issue of the heteroscedasticity problems. Okay, similarly, when you come to Park test, what Park suggested? Park suggested you take this u cap square and you convert this into ln u cap square. Okay, so is equal to ln u cap square n ln xi, dependent variable. This is the xi's. You take the ln of these things, ln xi. Okay, now what you have to do, go to data, analysis, regressions. Okay, this is the y range. Okay, and this is the x range. Some values are missing here, no? Let me check it. Okay. Okay, some values are missing. Okay. Okay, so data, regression. This is the dependent variables, and this is your independent variables. Go to OK, label. Now we don't need residuals. Okay, new worksheet. Okay, now you look at this equations, or now you look at this coefficient, whether this is significant or not. This is significant or not. How can we say it is significant? Look at the t value. If t value is greater than 1.9, minus 1.9 or plus 1.9, it means that t statistics at 95% level of confidence or 0.5% of level of significance. Okay, it is 2.29. That's why we can say that it is the slope coefficient is significant. Or you look at the p value, it is 0.025. It means that you can reject your null hypothesis at even 97 point something percentage. Okay, then the possibility of error committing is already 2.5 percentage. Okay, yes. So what we have to assume here? Here we have to assume that the slope coefficient is significant, and because of this thing we have to say that there is a possibility of heteroscedasticity problem in this data. Okay, yes, yes. Okay, but when you look at the graph, we cannot observe any pattern. Still there is a problem of heteroscedasticity. Okay, it means that if you plot the graphs, you always may not be able to infer something about the heteroscedasticity problems. Okay, here we cannot observe any pattern, but still there is a problem of heteroscedasticity as per the test suggested by Park. Okay, yes. Now we are moving to the third test. Okay, the third test is the cluster test. Okay, so cluster test is nothing but an extension of the Park test. Okay, so what Park suggested that regress the absolute value of u cap on the x variables. Okay, that will be very close to variance. Actually, Park suggested to take the u cap square on ln xi. Okay, ln u cap square on ln xi. Okay, and Gluster says that if you take ln u cap square and ln xi, okay, it will not be closely. It is not a good proxy for variance. Okay, the good proxy is, he suggested there are 8 different functional forms. Okay, there are 8 different functional forms, and the first 4 functional forms will be very closely associated with your variance if you have a large sample set. If your data is large, if you have a large number of observation in your data, okay, then the first 4 functional forms will give us a better results than Park test. Okay, so what is this? This is nothing but we are taking absolute values of u cap and we are regressing it on xi. Okay, we can check it how we can do that. Okay, I'm taking the same data. Okay, up to u cap. Okay, okay. Then what I'm going to do is I'm taking absolute value of u cap. U cap absolute values. Okay, so this is the u cap. This is not u cap actually, u cap square, I think. There's a mistake in this, I think. Minus, actually this is y minus y cap. This is u cap and this is u cap square. Okay, so we have to take this u cap absolute value. Okay, for that what we have to do is equal to abs. Abs means absolute values. Okay, and this is, okay, look at 20 minus 25 absolute values plus 25. You can do it for all. Okay, then what is the next? Absolute values of u, then on xi's. Okay, yes. Then the second option is root xi's. Third option is 1 by xi's. Last option is, fourth option is 1 by root xi's. Okay, so first of all let me take xi is equal to, this is our xi's. Okay, And next thing is root xi, root xi is equal to sqrt of xi. Okay, and next one is 1 by xi. Okay, 1 divided by xi is equal to 1 divided by this one. Okay, then the fourth option is 1 divided by root xi. Okay, is equal to 1 divided by 1 divided by square root of yes 1 by the square root of xi. Okay, yes, not 1 divided by, no. Okay, okay, now what you have to do, you take this as your dependent variables and you take this as your independent variables, or take this as dependent, this as independent, or take you independent, this independent, or this independent. Okay, so independent variable, there are 4 different specifications. You can take any specification. Okay, first let me do data analysis, regression. Okay, then this is your dependent variables and take this as your independent variables. Okay, okay, so look at this t stat, it is 15.69. okay, p value is something about 1.55. okay, so from this what we can understand here, the significant, if you look this around cost is 0. Okay, 1 point something e is there, so if you convert this, for if you format it for a number, it will get 0, I think. Yes, okay, so t stat is 15, it means that it is highly significant, and you have to conclude that this beta coefficient is significant and there is a problem of heteroscedasticity. Okay, yes, so this is what is called a cluster test. Okay, then coming to the one more test called Spearman rank correlation test. Okay, so why we are having different types of tests, because in each test there are certain issues. Okay, yes, so in the park test the main issue was the ln u cap square and ln xi is not closely associated with the variance. Okay, especially when you have a large samples. So Gluster, he has devised another method in which he has taken absolute values of u cap as the dependent variable and different types of variable as independent variable, and all these variable, all these functional form will be work better than park test, especially when you have a large number of data set. Okay, then the third test is the Spearman rank correlation test. Okay, it's a very simple test, and this test is based on t-test. Okay, so here what we have to do, here we have to fit a regression model like yi is equal to beta 0 or beta 1 plus uh, beta 2 xi plus ui, and you have to obtain the u cap. Okay, then you take the absolute values of u cap. Okay, and you take xi or y cap I and compute, or and you compute the different ranks. Okay, and you have to find out the Spearman rank correlation. What's the equation for Spearman rank correlation? It is nothing but 1 minus is 6 into sigma d square divided by n into n square minus 1. Okay, and this equation, this the Spearman rank correlation equations follows t-test. Okay, so its t value can be found out by using RS, that means Spearman correlation into n minus 2 divided by root n minus 2 divided by root 1 minus RS square, where df is equal to n minus 2. Here what we have find out? First we have found the Spearman rank correlation. Then from Spearman rank correlation we have derived the t-test or t value. Okay. The next is you compute the critical t values, and if your actual t value, that means this value is greater than your table value, then you have to reject the null hypothesis. Okay, the null hypothesis means homoscedasticity. Here the null hypothesis means homoscedasticities. Okay, so how we can do that? We can check it. Okay, for that what we have to do is, let us take a Spearman rank correlation test. Yes. Okay, so for this, for testing this Spearman rank correlation, I am taking a very simple example because taking a long example will be very difficult for ranking purpose. Okay, so what you have to do, I have taken the residuals, okay, then predicted y, then I have to rank this both. Okay, and when I rank the residual, what I have to follow is I have to take the absolute values of xi. Okay, so I have converted the residual into ABS, that means absolute values. Okay, is equal to ABS, you click the values. Okay, look at this value, all these values are positive, but you look at this, there are some negatives and positive values. Okay, but when you take the absolute values, all negative values will become positive values. Okay, so we have taken u. Okay, then I have taken predicted y. Okay, then the predicted y is ranked R1. Okay, look at, this is the smallest, then this is the largest. I have ranked 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is also I have ranked from smallest to largest. You look at which is the smallest one, not largest one, no? Which is smallest one? I think 0.8 is the smallest one. Okay, yeah. So there's a mistake here. Mistake means this is from largest to smallest and this is from smallest to largest. Okay, so I have to remove this, should be smallest to largest. Okay, 9, 8. Okay, yes. Okay, now it's okay. Then what you have to do? Okay, so how we can find out the rank? There is an equation for that. In Excel, there is a command for that. The command is, you click the rank function equal to rank, then click a value, okay, then comma, you select all remaining values. Okay, so rank, then which number you have to rank, comma, all the reference categories, comma, then you have to assign the order, whether it is ascending or descending order. Okay, then Excel will automatically rank the values. Okay, then you take the difference of R1 and R2, 10 minus 7, 3. Okay, 9 minus 2, 7. Then you take the d square and you take the sum of the d square. Okay, then what we have to do, we have to find out this is 1.68 is equal to 6 into sigma d square. Okay, this is n into n square minus 1. Okay, then this is sigma 6 into sigma d square divided by n into n square minus 1, and this is 1 minus 6 into sigma d square divided by n into n square minus 1. So you have got minus 0.07879 as your Spearman rank correlation. RS is equal to minus 0.07879. Okay? Yes. Now what you have to do? You have to specify, you have to find out the t values. Okay, so it is rs into root n minus 2. rs, see this rs into square root n minus 2. 2, 4, 6, 8, 10. So it will be 8 minus 0.2285. Okay, then divided by 1 minus rs square. Okay, so it's equal to square root, okay, square root of 1 minus this square. Okay, we are getting 0.9968. Okay, and if you divide with this value minus 2.2354, it is your t values. Okay, so this value is becoming minus 0.22354. This is the t value. Okay, then you have to find out the table values. How we can find a table value? T table or t critical values is equal to t inverse. T inverse 0.05 comma degrees of freedom is equal to 8 minus 8.5 minus 8.5. Okay, so here this value is greater than this value. Here your t value is greater than t critical values, so you have to reject the null hypothesis. What is the null hypothesis here? The null hypothesis is here is there is a homoscedasticity. Okay, so that you have to reject. Then your conclusion will be there is a problem of heteroscedasticity. Okay, so when you reject the null, you have to accept the alternative. So the alternative is equal to heteroscedasticity. So what the answer is, there is a problem of heteroscedasticity in this data. Okay, okay. Now coming to another test, it is Gold-Fed Condor test. This is Gold-Fed Condor test. Okay, so this test is also a very simple test. Okay, and this test is based on F test. Okay, so what we have to do under these steps, under this test? First step is you have to order or rank the observations according to the values of xi's, beginning with the lowest x values. Okay, so you have to arrange the data in from lowest to largest based on the values of your independent variable. Okay, then next thing is you have to omit the central observations. You have to omit the central observations. Okay, and divide the remaining observations into exactly two groups of consisting n minus c divided by 2. Okay, so what we have to do is you remove the central observations in such a way that the first part as well as the second part should have equal number of observations. Okay, and now we have two different data. Okay, one is with low variance and second one is with high variance. Okay, you find out the separate, you run a separate regression and find out RSS first group and RSS second group. Okay, yes. So the RSS first group is nothing but the RSS from a regression corresponding to the smaller xi's, and RSS2 is the residual sum square of the regression 2, and this is basically we have derived from the large xi groups. Okay, yes. Then here what you have to do is then you compute the F ratio. Okay, it is nothing but RSS2 divided by degrees of freedom and RSS1 divided by degrees of freedom, and this degrees this follow an F test with degrees of freedom for the first group and degrees of freedom for the second group. Okay, here df is equal to n minus c divided by 2 minus k. Okay, so what we have to do in this test, you divide the data into two parts based on the values of xi. Okay, then find out the RSS1 and RSS2, then you find out F ratio by dividing RSS2 with RSS2 divided by df divided by RSS1 divided by df. Okay, where df is equal to n minus c divided by 2 minus k. Okay, yes. How can we do that? Let me take the test. Okay, now you look at these values. Okay, this is y and this is x. Okay, here this xi is already arranged from ascending order, or arranged in ascending order. Okay, so there is no need to convert this into ascending order. If your x variable is not in a particular order, then you have to make such a way that the small value should appear the first and the largest value should appear the last. Okay, then now let me check how many variables are there, how many values are there. Only 30 observation is there. Okay, then from 30 I am taking only 13 and 13. I am removing this central observation. I am removing this central observation. Okay, so why I am removing the central observation? Because actually I want to check how the smallest group and the largest groups are behaving. Are they behaving the same way? Okay, so for that purpose we need only the extreme values. Okay, and that's why we are omitting the central values. You clear? Now what you have to do, you run a separate regression for this group. Okay, then you run another regression for this group, and what you have to find out, you have to find out only one thing, that is residual sum square. This is the RSS1 and this is the RSS2. Okay, so RSS1 is equal to, okay, then RSS2 is equal to this one. Okay, then df means what? Df is equal to n minus c. Total number was 30. 30 minus c, omitted observation is 4. So 30 minus c is equal to 4. Okay, 4 minus 2, n minus c is equal, n is equal to 30 minus c is equal to 4. Okay, then divided by 2 13. Okay, then this 13 minus k is there. Okay, this 13 minus k is 2, number of parameters to be estimated. Okay, here only beta 0 and beta 1, so it is 11. So df is equal to 11. Okay, then Yeah. Now F is equal to RSS 2 divided by 11. Okay. Then this is the denominator. What is that? RSS 1 is equal to 11. Okay. RSS 2 divided by DF and RSS 1 divided by DF. Okay. Now F is equal to F ratio is equal to this divided by this. I am getting 4.07. Okay. Then what have to do? You have to find out F table value. How we can find out? F inverse. Okay. Probability is equal to 0.05 comma degrees of freedom is equal to 11 comma 11. Okay. Here F table value is equal to 2.87. For decision actual value is greater than table value, we have to reject the null hypothesis. Okay. Here also we have to reject the null hypothesis of homoscedasticity. Okay. That means there is a problem of heteroscedasticity. It's a problem of heteroscedasticity. Okay. So this is all about goal-fed conduct test. Okay. Yes. Similarly, there is two more tests are there. Okay. The first test is Bruce-Spag and Goldfield test, or which is better known as PPG test. Okay. And this test is most useful or most used test in the research, or especially in empirical analysis. Okay. So this test, as per this test, what you have to do is, we have a regression with many explanatory variables. Okay, so we have a multiple regression model. Okay, so here we have a multiple regression model. Yi is equal to beta I x2, and we have many up to xk variable. And what we have to do is, here we are assuming that the variance of the error term is depends on explanatory variables. Variance of your error term is depends on some or all of your independent variable. Z2 means what? First explanatory variable. Z3, Z4 means first three independent variables, and Zm means up to last independent variables. Okay. Yes. Then using this model, how we can find out whether there's a problem of heteroscedasticity. For that, what we have to do is, first you run a regression and obtain error term u1, u2, u3 up to un. Okay. Then you have to obtain standard error of the regression model, sigma u cap square divided by n. Okay. Then what you have to do, you have to construct a new variable called pi, and pi is nothing but sigma u cap square divided by standard error of the regression model. Okay. Then what you have to do, you take this pi as the dependent variable and remaining all x as your independent variable, and run a regression, and you obtain the ESS. Okay. Then you take 1 by 2 into ESS, and this 1 by 2 into ESS is called theta. The theta follows the normal distribution with m minus 1 degrees of freedoms. Okay. And if the computed chi-square value is greater than the critical chi-square value, then reject the null hypothesis of homoscedasticity. Okay. So what you have to do, find out error terms. Okay. Then find out standard error of the regression model. Then divide u cap square with small or standard of regressions, and this is known as pi. then take this pi as the dependent variable and regress with all remaining independent variables, then take the estimated sum square, okay, then take 1 by 2 of the estimated sum square, and this 1 by 2 of the ESS will be our critical values or test values. If this test value is greater than critical chi-square value, then reject the null hypothesis of homoscedasticity. Okay, how can do that? Let us check how we can do that. Okay, yes. So the first step is what? You have to obtain U cap. Okay, so from this model I have estimated U cap. Okay, then U cap square, take its sums. I have take it sum, it is this much, okay, 11,000 something like. Yes, something. Oh, it's a huge value, I think. Anyway, yeah. Now what you have to do, you have to find out the standard error of the regression models. Okay, so this is the standard error of the regression model. Okay, then you have to find out small sigma. Okay, then small sigma is nothing but the U cap square averages. Then you find out the small p. Small p is nothing but this U cap square divided by pi. U cap square divided by pi. U cap square divided by pi is equal to U cap square divided by standard error of the regression models. Yeah. Okay. Then we have find out the pi. Okay. Then take this pi as the dependent variables and this as your independent variable. Then run the regressions. Okay. So this is the regressions, and from this regression, what you have to do? You have to take this value. This is the ESS, regression sum square. Okay. Then you divide this with 2.777. This follows chi-square distributions. Okay, then is equal to chi-square chi-inverse. Okay, 0.05 comma degrees of freedom is m minus 1. No, degrees of freedom is m minus 1. M means what? Explanatory variable. So divided 2 explanatory variable there, then minus 1 ones, 3.84 ones. Okay, so here yeah, here it is 2.77. Okay, so actual value is not greater than table value, so you have to accept the null hypothesis. Okay, so a null hypothesis here is there is a homoscedasticity. So homoscedasticity, then we cannot reject it, we have to accept it. Then here we have to accept that there is a problem of homoscedasticity, no homoscedasticity. Okay, so here we have to accept that there is no issue of heteroscedasticity in this problem as per this BPG test. Okay, so what is the steps? Let me repeat it. First, run a regression, take U cap, find out U cap square divided by sigma U cap square divided by n. Sigma U cap square divided by n. Okay, yes. Let me check it once again whether I am taken that sigma U cap square. Okay, is equal to, yeah, correct. This is the sum divided by 27, I think, or the average is 411524. 411524. Yeah, there's a mistake here. Okay, sorry. Yeah, so this is the correct answer. Okay, this is the small sigma. Okay. Okay. Now, yes, u square here. This is this one. Okay. Now go to data analysis, regression. This is your dependent variable, and this is your independent variable. Okay, label is there. Okay. Yes. This is y range is this y range, and this is the x range. Yes. Okay. Yeah. Now you take the ESS is equal to, this is the ESS. Okay. Then this divided by 2. Okay. This is the theta coefficient. Okay. 10.31. Now you take the chi inverse. 0.05 comma 1. Yes, 3.8. Okay, so here now you look at actual value is greater than table value. Okay, so here we have to reject the null hypothesis. Okay, so the earlier method, this method was wrong because the problem is this was wrongly selected. Sigma is wrongly selected. Okay, so actually sigma is not 79 something, but it is 41 something. Okay, so when I rectify this problem, then I am getting 10.31 as the theta. Okay, then 3.81 as the 3.84 as the table value. Here actual value is greater than table value, so we have to reject the null hypothesis. So here also there is a problem of heteroscedasticity. Null hypothesis, no homoscedasticity. When we reject it, then there is a problem of heteroscedasticity. Okay, yes. And the last test is heteroscedasticity or white test. Okay, so in this also we are doing the same thing. Okay, so what we are doing here, we are running a regression and taking the U cap. Okay, and taking U cap as the dependent variable and all remaining x as the independent variable, and we are multiplying n with r square and this follow chi-square distributions. Okay, then here the df is equal to number of independent variable in your regression analysis. Okay, so if you take the y test, yes, look at this value here. We are having only one experimental variable x. Okay, what you have to do? Yes, we have to find out u cap. Okay, and the u cap square. Then yeah, u cap is equal to alpha 1 something. So this will be equal to uh, u cap. Okay. X3, yeah, x2 square. Okay, yeah, here what we have to do is, here we have to, x2 is, if x2 is there, then what you have to do is, you have to take x2 square. Okay, then x2, x3, x2 square, x3 square, then x2 into x3. Okay, but here in our example we are having only one variable. Okay, we are having only one variable, so there will be x2 and x2 square. Okay, so look at, this is the x values. Okay, so x values, this is the x square values. Okay, then what we have to do, we have to take the sigma u cap square. Okay, then take u cap square as the dependent variable and x square as independent variable, then do a regression. Okay, I have done a regression and I have got these two values, and from this value I have got this r square. Okay, then r square is multiplied with the total number of observations, so I have got 10.03. okay, then if I find out the chi-square inverse, then I am getting 5.99. here also actual value is greater than table value, then we have to reject the null hypothesis. Okay, so this is what is all about White heteroscedasticity test. Okay, yes, so today we can finish here. So in these classes we have discussed how we can detect whether there is a problem of heteroscedasticity or not using graphical test, Park, cluster, Spearman, Gottfried test, BPG test, and lastly the White heteroscedasticity test. Okay, yes. So thank you.